Very good morning. Today we will go to transformer construction and EMF equation. The transformer construction, I'm going to the slide. See, this is the construction, the view is given here. There are two types of the construction. As per the construction, the transformer is classified into two. One is the core type and second one is the cell type. It has the main three parts are there. That is two windings and one is the core. A transformer consists of two windings coupled through a magnetic medium. As I already have told, there is no electrical connection between them, and the magnetic medium is nothing as this is the core only. Both the windings are working at the different voltage level. The two windings of the transformers are called as the high voltage winding, and second one is the low voltage winding. It has the common core. One of the winding is connected to the AC supply and it is called as the primary winding. In the last class I already have told this one. As per the construction, there are two major type of the transformer. One is the core type and second one is the cell type. This is the core type. In core type, what happens? The winding surrounds a considerable part of steel core. And the cell type transformer, the steel core surrounds a major part of the winding. This vertical part is called as the limb. It has two limb in the core type, but in the cell type, if you go, there you will get the three limb here. Here in the core type, this is the two limb is present. First the LV winding is done, then the HV winding is done. In between them there is the insulation is there. Here also the same thing. In the cell type, what happens? Here the sandwich type winding is there. Done. First is the LV, then again HV, then again LV. Here it is called as the concentric winding, but here it is called as the sandwich winding. The core type construction, we are using the concentric winding, but here we are using the sandwich winding. In the core type transformer, the path is only one path for the flux, but here the flux is classified into two or divided into two parts. One is the 5/2 and 5/2, but in the middle limb it is 5. In the core type transformer, the iron part used in the core is required less, whereas in the cell type, here it is more required. But in the core type transformer, the conductors required for the winding is more, so the copper requirement is more in the core type, but in the cell type, the copper requirement is less. For the core is made up of cold rolled grain oriented silicon steel material to reduce the hysteresis loss. It has the high permeability, which requires very less magnetizing current. Next is the EMF equation of the transformer. Since we are giving the alternating voltage, whatever the flux is created by it, it is alternating in nature. So I are representing this one is the phi max sine omega t, where phi max is the maximum value of the flux in wavers and omega is the angular frequency in radian per second. The EMF E1 induced in the primary winding by the alternating flux is given by the Faraday's law of electromagnetic induction. E1 is equals to minus N1 d phi by dt. This minus sign is for the Lenz's law, because this EMF always opposes this d phi by dt. So if we'll put the value here minus N1 d phi max sine omega t by dt, then phi max is the constant, so you will get the minus N1 omega phi max. The derivative of the sine omega t is the cos omega t. If you represent in other way, you will get the N1 omega phi max sine omega t minus pi by 2, which indicates that this induced EMF lags this flux phi by the angle of 90 degree. The maximum value of the E1 you will get is the E1 max, let that will be N1 omega phi max, because the maximum value of the sine function is 1. So you'll get the N1 omega phi max. It occurs when the sine omega t minus pi by 2 is equals to 1. So we are putting here E1 max is equals to 2 pi f N1 pi max volts. So if we'll multiply, the pi value is 3.141 and E1 is the RMS value of the EMF induced, then E1 is equals to E1 max by root 2, and putting all these values you will get the 4.44 f N1 pi max volt. This is the EMF induced in a transformer. Similarly, in the secondary side, if we'll find, then you will get the E2 is equals to 4.44 FN2 pi max volts. According to the above equation, these points should be noted. Induced EMF is directly proportional to the number of primary or secondary turns. Is it clear from these expressions? Induced EMF is directly proportional to the rate of change of flux of linkage. Induced EMF is depends on the supply frequency. As the frequency is constant, you can say it is the same. Only we can say the E1 is directly proportional to the number of turns and the rate of change of flux. Voltage transformer ratio. What is that? This is the secondary induced EMF to the primary induced EMF. This is the ratio of secondary induced EMF to the primary induced EMF. If we will divide this E2 by E1, we will get this is N2 by N1 or E2 by E1 or I1 by I2, that is K, is called as the voltage transformation ratio. With respect to that, the transformer is also two types. One is the step up, second one is the step down transformer. A transformer in which the output secondary voltage is greater than its input voltage is called as a step up transformer. Here the secondary winding number of turns of the secondary winding is greater than the primary winding of number of turns. So the secondary voltage is greater than the primary voltage, and if you will see here, N2 is greater than N1, so K is always greater than 1 for the step up transformer. Step down transformer, a transformer in which the output voltage is less than its input voltage or primary voltage, is called as a step down transformer. Here what happens, the primary number of turns, primary winding turns is greater than the secondary turns. So the primary voltage is greater than the secondary voltage. Obviously, the voltage transformation ratio is less than K. Okay, thank you.